If only I could allow people to actually interact, like call in. That would be really cool. No one else is here. Let's see.
Q&A. Oh, that's probably the Q&A for Google Hangouts.
This is really weirdly hard.
What are you
Oh,
trying to do?
I have two viewers. I would like to give the viewers ability to speak or interact with me some way. They could probably walk me through it if they could talk, but they can't.
Oh, you're muted. That's important. On the very, very top.
No?
Your sound is off. Very, very top, it's red.
Oh. I don't know if anybody can. I don't know where that is. Oh, right. Okay. Yeah, so Matt, if you're out there on the internet, and Ben too, I have done the Hangout on air. I may have to just switch to the non-on-air Hangouts, which are not recorded, but they seem to be much easier to figure out. Because I can see the people that are viewing, but even in the control panel, I can't seem to, let's see. I can't grant mic access to anyone. So if you're not in Fairbanks, you're lucky today because it's 40 below out there. There's actually weird icicles growing out the window.
Years. I get those in all my windows, but
Right, let's see. I keep bouncing between 0 viewer, 1 viewer, and it doesn't tell me who the viewers are, so that's go Google. And then somebody's messaging me. I can do a video call, but then the on-airness is broken.
Can you do 2 sessions with the same? Okay.
Am I just getting like terminally old here, or is like if I want to read? So I mean, Matt just chatted to me here, and yeah, I could call him. Well, the trouble is, if I do a video call, I mean that's a totally unrelated thing to the whole
Supposedly,
Hangout on
Google
air.
Hangout on air interaction. Apparently, there's some way to make the other people available to like ask questions. I don't know how. And the title of it was Improved Interactivity in Google Hangout on Air, but yeah.
Yeah, you would think in the control room you could take some of these viewers. Oh, maybe the problem is they're viewing via YouTube or something. You need to be accessing via Hangouts or something equally obtuse.
What's the very top left like thingamajig?
It's a
Recommended
pencil. Yeah. I probably just disabled it permanently.
Oh, to chat? They can totally ask questions in the chat, probably. Yeah.
You guys can ask questions in chat.
That's about as good as
it gets.
As it gets. So I mean,
it could be better. They could just yell at a question. Not that they seem to do that. So I hope my 2 viewers are actually can you go ahead and just chat a reply there? I don't know if that they're probably entering YouTube comments or something equally useless that will not show up here.
Did you send out a link to get to this? Or?
So when you make a Google Hangout on air, you give it a list of people that you would like to send the link to, and I sent them the link. So
you can send like someone else in here the link and we can
Link to share from the Hangouts window. No, not. No, let's see.
Oh, you can embed.
You need the event, not the YouTube. Okay. Right. This is just horribly broken. Okay, so.
Disappointed in.
His name is Matthew, of course, so that.
You want to send it to me too, so I
Sure.
can just test it. Cool, that's right.
Yeah.
Sorry.
Okay. Google is it's destroying my faith in Google.
Oh, it's on Google Plus. Oh yeah.
It's
there's
so
chat.
Google Plus is somehow like infected with the madness of the Hangout. I mean, Hangouts, YouTube, Google Plus, all of there's some dense
I said
diagram.
something.
Okay.
You don't see it.
Nope.
Awesome. Oh, it's on Google Plus. You see the comments on Google Plus. That's got things.
Interesting. Yeah. And in the control room, I have no anything. Yeah. Anyway, hey, well, we had class, right? So hopefully there's some perception of this, or it's recorded or something. So, right. Oh, and hey, here's another window.
Sorry. If you go to the Q&A, like on the window, there's a button that says Q&A. 2 down. Yeah. They've been asking questions. There you go.
Yes, I can now see that. Hopefully you can see me seeing it. Okay, I guess we have students there. Yeah. Gosh, that's just horribly broken. Anyway, Roy. So today's lecture is about information, and actually what I want to do now, I think, is just not project anything. So
It's still showing, but yeah,
you'll have to watch on the little screen now.
that's right.
So, information theory it's actually fairly crucial to crypto. I keep using the terminology without even meaning to, right? Like, what do we mean by entropy? Right. We always talk about like you need a higher entropy passphrase, for example. What does that even refer to?
More random.
Chaos.
More randomness, right? Chaos is good. Chaos is unpredictability is that's the only thing you got to save you, right? So what you want is you want chaos. So we want to make sure that our key is unpredictable. That's sort of the fundamental thing that we want out of there. So anybody know the definition of entropy? Turns out you can measure it. What's it?
Mathematical one?
The mathematical one. So you measure entropy in bits. Lots of ways of doing it. But,
It's the sum of probability. I don't know.
so Shannon's definition of entropy, which is kind of a big one. I take the probability of getting this message. So in other words, the entropy in bits of a message. Take the probability of getting a message. I multiply it by the negative log base 2 of the probability of getting a message, which is like what? Probability is between 0 and 1, right? So coordinate axis, if I have the probability here, the log of the probability runs like that. Crosses through log of 1 is 0. So if I take negative log, it's doing this. I multiply it by p, which is doing that. So the product of these things is some sort of bathtub shape, upside down bathtub curve. So that's kind of interesting. So maximum probability. So the maximum information. So this is the information from a message, right? So info from a message. Measured in bits if you take the log base 2, which is kind of curious. So you can actually you can play with this definition. So we got and that comes right back. All right, good.
I'm confused by this definition.
Yeah, it's not real obvious where the heck that comes from. So you can ask, for example, I defined a function named info, and info takes in probability. So if the probability of getting a value is 0.5, then the information I get out of that is actually also 0.5. The probability of that message is 0.1. Right? So you can vary these things around. So if I have an extremely low probability, I get an extremely little bit of information out of that. Maybe, okay, semi-plausible. If I have an extremely high probability, I also get a really low amount of information out of that message, right? So if the message is always 1 with extremely high probability, I basically don't get any data out of that. If the message is always 0, right, and the probability is really low, I also don't really get any information out of that. So Shannon was working on like, I've got a wire connecting 2 guys that have to communicate. How do I encode information on the wire? How does each side figure out what the heck they have? So you can put a message on the wire, and he was looking at how much information can you get out of a given message. So the idea is you hit the maximum information per message if you have exactly 2 messages, it turns out. So if I'm operating in binary, there's 2 possible values, right? I could send a message of a 0 or a message of a 1. What are the probabilities of that? Well, if they're 0.5, 0.5, then it turns out that the information I get is 0.5 out of the 0s and 0.5 out of the 1s. So I get a total of 1 bit, per bit that I send down the channel, which, okay, 1 bit of entropy communicated per bit of information going in the channel, which sounds like, well, how else could it happen? Well, it turns out, if I look at the information of, I take the information of 0.1 probability and the information of a 0.9 probability, and what's weird about this is that you get 2 values, right? One is 0.3, one is 0.1, and I only get half a bit of information out, half a bit of entropy, because I just don't have enough. I'm still sending a binary data, but I don't really have, right? Most of the values are 1s. I'm hardly ever getting 0s. The fact that I hardly ever get 0s means that 0s are really valuable, but I hardly ever get them. And so the more biased your channel is, the less information you're getting out of it. Even though you're sending, so this is kind of a cool definition of this stuff, right? So if I've got 1 out of every 1,000 bits is a 0, I'm getting way less than 1 bit of entropy transmitted per bit of communication. It's a sort of funky. There's a lot of weird, slippery concepts today, actually. So one of the really slippery things about this, what does it mean to have a probability of a message? I mean, that's kind of a weird thing. Actually, I was kind of surprised that, like, what does probability even mean? It's kind of, there's apparently like 4 separate schools of thought on this.
We just went over this.
Oh, cool! Yeah. What do statisticians think probability means? It's pretty essential to the field, right?
We didn't go that far into it. There's a lot of handbook.
So I'm not a statistician. My understanding of frequentist makes sense to me, right? That, like, I say the probability is 0.9. If out of the last 10 tries, 9 of them were hits, so that means probability is 0.9. Right? So frequentist, I look at past data, like every time I've done this before. Now the problem is you can't actually do this if there's only a 1, right? So if I have a coin, right, and one side is really heavy, you might think it might be heads more often, right? But if no one's ever flipped it yet, frequentists can't really tell you anything, right? So hypothetical situations, you can't really say anything that the frequentist model.
Is there probability for stats, like a degree of confidence in the answer you receive?
That's currently in here. So, yeah, degree of belief.
That's basic probability.
The principle of indifference is saying, this is kind of an interesting physical one. It says, like, if you've got heads and tails or your states, if they're indistinguishable other than the name, it's 0.5, right? And similarly, if I got like 3 possibilities and they're all indistinguishable, it's 0.3. That's what 0.33. That's what we mean by probability. So indifference, right? We can exchange these things. This seems surprisingly what?
Metaphysical.
So here's a big problem, right? If I say, okay, yeah, this is the probability of getting this bit or something,
what's the probability my name is Orion Lawler, I have a PhD, I live out in Fox? The probability is essentially, well, I don't know, is it 1 or is it 0? Because this is an extremely unlikely combination of circumstances. There is one other Orion Lawler out there, no PhD, lives in California, he's a banker, right? So, I mean, what?
Exactly.
Right, because that's a lower entropy situation, right? This is, I mean, this is kind of surprising, and he's lost on Google. Sorry, man, I'm just totally blocking. So I mean, what is the probability that this actually ended up in this room, right? So from some point of view, right, from sort of the frequentist perspective says like, well, okay, if we take the set of situations where we're in this room right now, there's only one of them, and hey, we're all in this room. Probability is 1. What the heck, right? Whereas if you sort of had said like, you ask 1,000 years ago, what are the probability of people with these names and these attributes are going to end up in this room and this room's going to exist? It's 0, right? I mean, the Chapman would have been down the hill or something, right? And it's just would not have worked out this way. So I mean, is the probability 1 or 0, right? That's a pretty big sort of question mark to have in your head. And unfortunately, it's the same exact deal. If I have a message of hex 61, I think is the example I use collection of, right? That's an ASCII A. What is the probability of that? Depends on how you think of it, right? So you can say, well, there's 8 bits, and that one has to be a 0, and that one has to be a 1, right, etc. So you say, well, it's 1 out of 256, right? That's the probability of it. But if you're sending, I don't know, if you're sending ASCII English text or something, A is used a lot more often than that. If you're sending hexadecimal numbers, it's used even more often than that. If you're sending a string of A's that just keeps going forever because the program's broken, probability is more like 1. Right? So I don't know. Probability starts to get. There's some actually really interesting work in physics of all places, where they're actually so the hypothesis called constructor theory is that information is actually sort of the fundamental particles of the universe, right? That the bits were sort of there before the particles that represent them or something, right? I don't know what that means. So apparently there's a lot of debate as to what this probability actually means. It's easy enough if, for example, we have a program, we can run the program again and again. Oh gosh, viewer versus presenter.
That question was like 30,
okay.
like a minute ago, actually. And your presentation is like 5 minutes behind. So.
Cool. Yeah. Google Hangouts on air. Right. So questions about probability? Yes. So the real deal, right? You have to ask if I have a program and the program spits out stuff with this probability, right? And the real question from a computer science point of view, I really want to get 1 bit of entropy for every bit I have in a computer. The way to do that is I have equal probability on 0 and 1. It sounds surprisingly easy. How easy is that to actually pull off, right? Equal probability, 0 and 1, and ideally be equal probability under any sort of circumstances.
I mean, it depends on what you want to do.
If you're sending random data, sounds really easy to do.
Yeah.
But like messages, like human languages have, show up more, right?
Human language is actually, so interesting fact, right? If I got, 1,000 bits, right, so your password, you've just typed in 1,000 bits worth, it's probably not 1,000 bits of entropy. It's probably way less, right? And this is because human languages have lots of redundancies here, right? And I'm getting blinking, but that's why this is.
So sorry, I just wanted to verify this. You said the more biased your algorithm is, then the less entropy your message has when it's.
Yeah. So this sort of makes sense, right? If you tell a computer, hey, make up a key, and it's like 0000000000000000001, then it's like, is that really the best key you come up with? Right, it's just, it doesn't seem that random, right?
But that's
It's
possible.
like-
Just as
It seems like it has to be
all the other ones
possible.
that way.
It's possible you do, yeah. So again, this is like last time. You know, if it really is truly random, it's guaranteed eventually come with really non-random looking, right? I keep worrying about this for the net run passwords, right? Auto-generated ASCII texts, and I'm really worried it's going to be really insulting to somebody. And it's like, in fact, sadly, it's inevitable that it's going to be really insulting to somebody, right? That you keep like every year we keep, giving 50 new passwords or something. It's gonna. I should probably like alternate letters and numbers or some way of guarantee that reduces my entropy. That keeps me from hopefully. Of course, then it's going to be like, yeah.
Too polite to have a secure password.
Yeah. So if you look at human beings' passwords, the situation is atrocious. So good blog post. So this guy analyzes all of the dumps when they find that they pull down lots of passwords on these things, and my network is extremely slow. So like the 10,000 most common passwords, and I've already got this on my drive somewhere. So you can basically fire this thing up, and
That word map.
of the no, this is this is a biased set, right? Because these are of people whose accounts got cracked. 30,000 of them have the password, right? 12346. Actually, I was surprised to find that 12346 is like 5 times more common than 1234.
Because 5.6 way more secure.
It's pretty commonplace the passwords have to be at least 6 digits long.
Yeah.
So I've actually had so this is kind of surprising. This kind of stuff, it's so common, it's actually guessable. We had so ASUAF used to run a web server, and somebody had an account name of they're an Asian a transfer student. Their account name was Catherine. Right, their password was 123456, and just sort of out of the blue, you could see this in the logs, right? They're trying account name starting with A, account name starting with B, account name starting with C. They hit Catherine 123456 with the password, bam, they're in, right? And what they do is people could make like PHP scripts, so they then use the PHP vulnerability to get to pull down a bunch of tools. They pulled the database. Bad news, right? It's kind of game over at that point. It makes me realize, one common thing people do is you run cracklib. Anybody use cracklib? So its job is to crack the passwords on your own machine. You, the sysadmin, will actually try to decrypt the passwords on your box, just because if you can do it, then any random person on the net is going to do it. So try and guess your own passwords, right? So this is actually common enough. And 123456, that's guessable, like just randomly across the internet, and that's the way to get an account shell on a box.
We set up
John the Ripper.
no, it was a honeypot for IDS last semester.
Yeah.
And when me and Bucky were going through our logs,
Yeah.
a lot of attackers started with a dictionary attack that had
Yep.
all of these front loaded
Oh, yeah.
in the first 40 guesses.
Does anybody have an EC2 server?
Mhm.
I've been running EC2
Yeah.
for a while. Sometimes I looked at my crypto logs. I'm like,
Oh yeah.
yeah, there's like a ton of Chinese addresses in there that list.
Yeah.
In that order.
Yeah.
Dr. Hayes set a honeypot up, and within like 10 minutes, he already had someone into it. So
It's amazing. Yeah. Yeah. So the big problem, right, is that these are, and several are on principle, but
I don't believe this list, because let me in on my honeypot. I had the password "let me in," and no one got it.
No one tried.
I left for like a week straight. No one guessed it. I was really disappointed.
that we're requesting our honeypots are pretty awful though.
I was surprised. These guys actually got a shell in a box. They had like pretty extensive access because they had SSH. They copied over an IRC server, which I think they use for command and control and to just hang out with their idiot script kiddie buddies. And then they copied their scripts. So we actually got like the list of passwords they were trying, the list of account names they were trying, and there were only 3. It was like password 123456, 1234. It was like the top 3 there. And that was enough to kind of get them across the internet, because looking at the IP addresses they came from, somewhere in Denmark that probably was not actually, that was just another cracked box. So I don't know, frustrating. Yeah. So our goal is to avoid that stuff, right? So you want your n-bit key to really have 2 of n possible values. Now the problem is, if it could represent 2 of n possible values, but you chose 0, This doesn't help you, right? This is the whole reason for the entropy thing, right? How easy is it to make the probability of a 0 and 1 actually equal? And how can you verify this? So it's easy enough. Have it generate a bunch of keys, right? See how many zeros you get, see how many ones you get. It's not going to be exactly 0.5, but pretty close. It's good enough. How good is that? And this has happened so many times. It's actually sort of.
So for key generation, you got to make sure the inputs are like.
Where do these inputs come from?
Yeah.
Because it's easy enough to get zeros or ones, but the way you do it is you say, yeah, 0, 1, 0, 1, 0, 1, 0, 1. What's the probability, right? And that, so you've just output a 1. What's the probabilities look like? It's deterministic. You're gonna get a 0, right? That's no good.
Seems like you just take your password, take the number of bits, and then you can just generate possible bytes for each position that have equal number of zeros and ones. Yeah.
Direct permutation of the password.
And then just find ones that have equal zeros and ones.
Yeah.
I make that sound really easy, but that's what I got.
Yeah. So in practice, here's the big problem, right? I want to make a key. So basically, if so what's the input data? So I want to end up with a key that has this property that nobody can guess, right? I use zeros for the keys, ones for the keys. So I can take the password and I can basically generate the key. Now the thing is, the password has nothing like enough entropy, right? That this is the human readable passwords, human typable passwords are extremely low entropy, right? I mean, if it's alphanumeric, you're still in low ASCII, right? Even if you use enough like control characters. I mean, the thing is, if you want to see what true binary data, right? You cap something zipped, right? Something zipped just laying around. I don't. Yeah. So right. So that's what it's supposed to look like, right? And this is and okay, my terminal actually survived. Wow, that's cool. So right, it's unprintable, 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 like a backwards L. Control character 14, unprintable, unprintable, open parentheses, unprintable FGIA, unprintable, unprintable. I mean, occasionally it'll hit like a carriage return. This is not an easy password to type in or remember. There's an extremely good, let's see here, right there. So this is this famous XKCD on password strength. So it's surprising to me that this is what people recommend, right? That like take a common word, which gives you, or take a word. There's definitely, so this is a number of bits of entropy they estimate. If you swap the order on doing some things, that's 1 bit. That doesn't help you much, right? You have a numeral. Actually, if you don't know it's a numeral, you're getting a few more bits there. But if this is like your standard thing, I mean, it's like this is just not that much entropy we've added. The substitutions are really bad, actually. John the Ripper, for example, will transform lowercase a @ sign. It'll transform lowercase to uppercase. It'll take a letter 0 and replace it with a number 0, right? Letter O to number 0. So it's easy enough to do the stupid substitutions. You don't gain much entropy at all, right? Is it caps or not? Uppercase is 1 bit worth. And this has really gained you very little, right? So we're like maybe 28, 30 bits of entropy, which is totally crackable. And I mean, it's crackable even if they can just like hammer on your web server and say like, is this it yet? Right. So if they can hammer on the web server, maybe 1,000 accesses per second is doable. It depends on is it on AWS or is it a local server. Local server might be faster. AWS might be slower. You could put rate limiting in and try and drop that down, but now, okay, instead of taking 3 days, it takes a month, but still, you could try a lot of possibilities. It's much, much worse. If they can download the hash of the password, or if they have some way to check the password locally, they could say, run your encryption algorithm, compare the output they get with the output they saw going across the wire. Suddenly you're up at, you have to worry about really big password cracking speeds. So for example, Pico Computing, which is kind of a cool little, they sell these little like business card sized FPGAs, and then you can just pack a huge number of them into a server. So like they sell a little cluster where, let's see, it's a 4U server. It'll do DES at 1/3 of a trillion keys per second. So, 10 to the 10 to the 11 and a half power, right? So you're definitely, and that's what 30. How many bits of keys? That's 2 to the 35th or 2 to the 36th, right? That's so. I mean, and that's per second. And this is with a fairly small size thing. If you imagine like a data center full of these things. So, for example, if government agencies after your stuff, it's the cracking rates really get crazy. So I know CCDC, right, the National Computer Security Competition, they apparently brute forced all passwords up to 12 characters long, and they burned $3,000 at AWS, apparently just renting CPU time to crack passwords overnight. And so now there's 12 character password is that's pretty long, right? That's considered pretty dang good. And then they were brute forcing explicit enumeration of everything, which is really scary. So the problem is, if it's truly random data, human beings have a dang hard time remembering it, right? If it's just this gibberish, minor gibberish, it's just not that memorable. So the XKCD's recommendation here is we just take different words. I don't know if this is, 44-bit century is actually still not really that good, but it's better, right? Yeah. So we actually did 5-word, yeah. Or if you're now willing to combine, one of the things about doing this is if you publish, for example, that we're always going to do lowercase space, then it is actually, enumeration style attacks are still theoretically possible. If there's really only 2 to the 44th words, then that's the limit. So if you just put like a dot between 2 of them, or some minor modification you can remember, unless they can guess the minor modification, it gets harder for them to guess how you've assembled your passwords. Right. So yeah, the frustrating part about this is you end up with. So I was trying to do this for my bank accounts, and it doesn't work. It says like your password can't be that long. In other words, you'll never remember that, you stupid user. Right? 16-digit passwords. Several sites have limits like that, which seems silly. If you want to use like 10 words out of a dictionary, you may not find very many places where you can, in fact, use that. Right, and so memorable passwords hard to actually come up with random stuff. Here's the other problem, and this is again straight from XKCD. So, Mr. Black Hat, the example of all that's wrong. If you reuse passwords, right? I can't imagine the number of sites that now have my default throwaway password. It's a lot, and the problem is if you use that on other things, well, okay, so don't use that password on your bank. Don't use it on any service that you actually care about or could be explicitly attributed to you. So yeah, big danger. So then what? Well, Black Hat doesn't actually know what to do. In that situation, so he's claiming he's already done that. Yeah, it actually is a little bit worrisome. There was a big the Russians published this list of 2 million usernames and passwords or something, and presumably collected in this way. There's a lot of I'm amazed how many websites on the back end are PHP script that says take your password in clear text and then put it in the database, because no one could ever read our database, because our 10,000 lines of PHP certainly has no SQL injection attacks whatsoever. Right? That's what they're hoping, and it turns out that and frustratingly, I keep noticing there's all these free database backends, right? Google Forms got. Just seeing one, Google Form service or something. So you can basically you can upload data into some storage, and it's basically a cloud accessible from anywhere, potentially not even authenticated, right? It's just a data store service, right? You just publish anything you want on that thing. So there's literally no protection on all of the passwords out there, right? So yeah, what do you do? In other words, we know passwords are actually not that great a source of entropy. We know that they're not the good a source of entropy in the first place. People are trying to steal the passwords in order to crack the things.
In other words, you really can't use the password directly as a key. So what do you do?
Your IP is used for random.
Yeah, so the conversion from password to key does not have to be the identity. Right? It can be anything. So for example, it's really common. You want to use the key to encrypt some data, right? To keep something secret. So you could actually take, let's see. So if I have an encryption algorithm already, I could use this password to encrypt like zeros, right? So I take zeros. I use password as a key. Well, this is not a good key, right? Because it's too enumerable. So I use RC5 or something, for example, and I'll encrypt zeros using the password to get the key, and then I'll use this as the key to encrypt the actual data. All right. So now I take the data. So two-step. Right? You could actually repeat this about 50 times. Plenty good too, right? So I'll take zeros, I'll run through RC5, and now it's kind of, it wasn't a very good key, so maybe there's some correlations there that shouldn't be. So I just repeat the process, and I repeat the process more and more. So if you're the attacker, how do you undo this? So you're going to start with the ciphertext. So here I have the ciphertext. That's the plain text. You have this. You want to know that. So you have to say, is it password? Nope. Is it 1, 2, 3, 4, 5, 6? Nope. Repeat. Right. So in theory, they can do that. The number of iterations you put here is basically linearly slowing down the attacker. That's not as good as the sort of exponential slowdown. Like if I can just get one more bit out of the passphrase, that makes it twice as hard for the attacker. And that's if you make your passwords minimum length of 12 characters instead of 8, and suddenly you've made it thousands of times harder, which is really good. Right? To change that, I get the impression a lot of password rules, like it must have at least one special character in the third place, are designed explicitly so that you will not have a password like that already. You'll have to make up a new password somewhere. Yeah, so they're trying to prevent password reuse. Actually, on NetRun, I don't let you reset your password because I don't want real passwords. I'm scared. I don't need that kind of responsibility. So your NetRun password is this tiny little thing that, yeah.
It's just plain text anyways over the net. Do anything with that?
I finally upgraded to HTTPS, so you can now access via HTTPS. I have not gotten around to closing off the plain HTTP. I need to do that at some point, or do a redirect. Easy enough. Although I think it's probably too late once they see the web page. Yeah. So the bottom line, right? You want to have it's kind of frustrating. AES needs 128-bit key. Nobody has 128-bit key laying around. Not with really 128 bits of entropy. So somehow you have to munge the key beforehand, right? Lots of ways to do that. Turns out you can measure entropy. We still don't really know. I mean, I haven't explained what it is because I'm kind of unclear on the concept. I mean, this probability, we can. This is by no means a foolproof method. But I can take binary zeros, like I can take a mega binary zeros. I run it through gzip and it's 1K, right? That indicates there may be some redundancy in there, right? The entropy of this was really not as big as the file size might indicate. I mean, if it's all zeros and you know it's all zeros, it really should be 0 bits long. And actually, I was impressed. bzip2 is able to must have a special case for this because it'd be 45 bytes. And then there's essentially nothing. If you look at like Wikipedia, which is arguably the lowest information content source out there. It zips down to about a third of its original size, right? H.P. Lovecraft, which maybe I was getting, religious texts, always, I didn't really want to open that can of worms. So H.P. Lovecraft is as close as we'll get. So again, 30%. If I have a random ASCII hexadecimal, I was actually quite surprised by this, right? That it's not, it's just hex, right? It's your 10 digits and 6 letters. You'd think that would be much smaller than the actual 26 letter alphabet. It's not. It turns out because it's truly random.
I mean, it's if I can lose a quarter of the data or 2/3 of the file size and still have more or less the same thing, that means there's only like 2 or 3 bits per byte, right? So each letter is only giving you another few bits, which actually, and this is as far as zip could come up with, and it's not clear what is the real entropy of this thing. So the big problem, right, with this style, I mean, it's just very hard to define these things. Sure. For example, I might take, so here's some random digits. So here's our, is that visible? A slightly bigger version of that. So how random are those digits? In other words, how much entropy is there?
See lots of sevens.
There are a lot of sevens.
Are there a lot of sevens, or do you see a lot?
I see a lot of sevens. That's
There seem to be a lot of places where the same number is right next to pairs of 1s and 4s and 9s and 7s.
but we're only seeing like part of this file, right?
I'll give you a hint. Does anybody see a 0?
Well, this is obviously made by a mathematician, so there would be no zeros.
Not even like in the middle of it? I mean, yeah, I see leading and
This is-
trailing, it would be there.
This is easy enough, right? /0. Oh, not found. Hey, problem.
It's only the natural numbers apparently between 1 and 9.
Did you just make this by?
I made this. Yeah.
By just replacing the 0 character with new lines?
I used said. Yeah. I replaced the 0 character with nothing. One other transformation here. I mean, seriously, this happens 1 out of every 10 times, and it really wasn't. I mean, it's not obvious. So there's another like kind of painful like whoa every time.
Are these like numbers from something, or
These are numbers from something.
are these like IP address?
It's actually straight from Dev Random.
Okay.
It should be really good entropy.
Oh, Dev random, like you random?
/dev.
Dev U random. Sorry.
Okay.
Yes.
Oh, you want to go this for the time.
There's a We'll talk about this in one sec. Yeah. So look at the first 4 you see on each line. It's the first 4, not every 4, because evidently I screwed up my regex.
Are there at least 2 numbers that are always no? Every 962. No.
So the first 4 in every line is 2 4s.
Yes.
First 4 in every line is 2 4s.
Yeah. So it's
And many other
Double.
fours are double fours.
doubled. I think any other double 4s are by chance. So here's the surprising thing about this. So I'm not doing this to say like you should all like study until you're like a Rain Man and you can just look at a page of numbers and like no zeros, no
Not
zeros,
random.
definitely
Not
no zeros. Yeah. But the deal is humans are bad detectors of deviations from perfect entropy. Right? If you look at the histogram of the digit frequency and you see, oh yeah, 1 occurs 4,000 times and 2 occurs 4,392 times and 0 occurs none. Problem. Right? You can see that hey, there's something wrong there. So, how many bits have you lost by doing this? I mean, how much entropy have you given up? So suddenly we have a way to actually evaluate this, right? We have an equation. Sure. Somewhere. I had an equation. So information function info, I guess now I'm gonna have to have, I'll just do it the same way before. I guess I define functions in MATLAB. Okay, function that info. I say ret is equal to p times minus log of p, and it's log base 2. So I verify that it works by checking 0.5. Okay, great. How much information do you get from a decimal digit, right? So each message, right, probability 0.1 gives you 0.3 bits, right? I have 10 of them, so I have 10. So you say, whoa, 3 bits. So there's
You get
10.
1 bit per. Can you get 1 for the first thing, not half?
I should, there's 2 messages.
Oh, right.
Yeah, each of which have probability 0.5. So my
Yeah,
total
yeah.
information content is 1 bit per
sorry,
bit.
sorry.
How many bits per digit? Well, okay, there's 10 digits, each has probability 0.1. So I have 3.3 bits per digit, right? So decimal digit, 3.3 bits. If you want to know like hex, well, okay, so hex, yeah, message starts to get a little weird, but so 16 possibilities for hex, right? 16 possible digits. If 16 digits, right, there's 1/16th probability of each digit. I have 4 bits per hex digit, which makes sense because it's 4 bits per hex digit. Yeah, so information carried by a message, and then if I want the information on the channel, what's the sum across all the possible messages using same before.
Oh, that's the probability.
If they're all
Make
equal.
more sense.
So here's the deal. If I have a decimal encoding, but I've lost one of these, it's actually what do I end up with? It's actually now it's a base 9 encoding essentially. I'm down to 3.1 bits per digit, 3.17 instead of 3.32. So like losing the zeros really wasn't that big a deal, right? In an information theoretic sense, losing a few digits doesn't actually cost you that much. It's kind of surprising. So I do this for net run passwords, for example. I don't allow 0 and capital O, either one. Why not?
Confusing to look at.
Because I'm freshman.
There are no zeros.
Freshman gets the email and they type it in and it doesn't work. And they're like, then they email me.
You're only saying that because this is a 400 class.
Yeah. So it would be frustrating if it's like, yeah, your password is something, because I mean, if you use both letters and numbers, you're going to have really difficult, like, what do I type there? Is it even possible to type that in, right? I mean, lowercase l and capital 1 are virtually indistinguishable in most fonts. So yeah, so I just say, nope, none of those. How much entropy, but so you used to have 56, 66. Uppercase, lowercase, what's it? It's 2 times 26 plus 10. All right. So I've got lots of entropy there. So 2 times 26 plus 10. Some way to duplicate this, but I don't know how. So I had almost 6 bits per character. She's getting pretty good. That's closing in on like full. I mean, if it was full byte, right? Type this untypable thing. Good luck, kids. That would be 8 bits. So I've got 6 bits is doing okay. Now the deal is I'm going to give up like 5, right? Uppercase, lowercase, O, capital L. Let's see, lowercase L, capital I. I mean, there's a list of stuff I just do not allow, and I lost like a 1/10 of a bit or something, right? Which is doesn't matter much, right? A few percent is I'm willing to give that up to make this thing easier to remember. So being able to measure how much entropy is actually there is actually really valuable, right? That this is something that lets you rationally evaluate, different password policies, right? If we restrict, so here's the paradox about this. From the computer's point of view, this is more bytes, and this is clearly, there's just more data to store in your brain, humans, than this. So to a computer, this would be clearly easier to remember, right? In fact, heck, why are all these printable, right? You should have some control characters and some crazy Unicode combining stuff, right? And it's all just as good if your data storage is in binary. But if it's a human being, I mean, basically what we've done here is we're using more bytes, but this is easier for human beings to remember, right? And I mean, Mr. Monroe's point is that passwords are for humans to remember. So hey, if there's no other takeaway from this, please, unlimited password length. If you could possibly do it. I mean, don't assume that because somebody pastes in 1,000 characters that they cannot paste in that 1,000 characters again from scratch. So
I think it's denial of service, though. It's like, I just uploaded 10 gigs of password. Ha!
I think you start getting entry returns after a while of like how long it has.
Yeah, I presume. And I guess, yeah, so the big problem is like, even if you were a Rain Man, if somebody asks you to just like repeat on command this meg of stuff, you're gonna have to type it in perfectly, right? All sorts of other errors start creeping in there. And then like, what is the chance that you'll actually have, it'll be,
This is a beautiful one, actually. Sure. I have lots of different digits, right? So this example of sort of random numbers is actually missing like these different digits, right? So that's the one we saw. This one, it has zeros.
Very
Yeah,
nice.
it's
Very
funny how
nice.
the zeros just leap out at you, right? Once you've been burned on that. This should be pretty close to random, except I realized doing it that it's random numbers between 0, or let's see, random 64-bit integers. They were actually, it turns out there were 2 of them. They were signed. So I think you're okay, except that leading digit. Leading digit, hey, what do you notice about the leading digit? It's never 0. It can't be 0. It's a leading digit. Right? It would just be shorter. I mean, like these are the cases where it should have been 0. Yeah. So I mean, so generating these things, it's hard. How much entropy in this? So you notice, so it should be. So there's a 0 right at the start of the line, so that would be good. There's zeros all over. You can look at the 4 thing that. So I haven't really munged this at all. I mean, this looks like, you know, pretty dang good. I suspect if you zip it, it's going to be pretty close to the entropy of decimal. So let's see. So we went from 10K to 5K, which, okay, so actually that's slightly better than you might expect from, I mean, there's 10 digits. It should only have 3.3 bits per 8-bit byte. Right. So you might expect it to be a little less than half size after zipping, but it's actually more. So hey, it's pretty good, right? Turns out those things are the digits of E. You might have the same deal if you have the digits of pi or the, I don't know, your favorite number is the square root of 3. What's weird about these things is that, I mean, like you pick an irrational number, in some ways, from some point of view, it's a really good random number generator, right? That actually passes virtually all the statistical, it has to pass all the statistical tests of randomness. Is E random? I don't really know how to define that. Yeah. I mean, no, because if if someone is trying to guess this and they know that you have a degree in math, they'll be like, wait a sec.
I always wanted to try that, like the calculus upstairs. It was like, if I was a math person, 314.
The real question is who installed those?
Yeah.
So is this good? So I don't really know how to define. I mean, what is the probability of E? It's just E, right? It's just this fixed number, right? So from, again, it's one of those 1 versus 0 things, right? But it's like tough to define. So this is an example of pseudo randomness, right? That I mean, E is this constant of mathematics. We know exactly what it is. There's no entropy there. There's no randomness from one point of view, right? If as soon as you say E, that one letter has sort of conveyed, right, or pi or square root of 3 or pick our irrational number. So what does that mean? So there's a pretty good definition of randomness that the program to generate it, if there's a program, would have to be about as big as the data. The thing about E is it has all these nice mathematical properties that make it E. That means you can write a tiny little program and just start spitting out E. Same deal with any irrational number, right? I can have some approximation that's basically converging on root 3, and hey, so that could be a very short program. So yeah, now
how do you find out that you need a huge program to do this? Well, without being able to search all over all possible programs, nobody really knows how to do that. So it's frustrating, right? No way to tell that your random numbers are bad other than having somebody say how they're bad. And until they do that, there's no way to really know how, if they're bad or how bad they are. So what do you do if you need random numbers and you're in the nice situation where you can actually have a computer generate random junk? Where can you find real sources of entropy on the computer?
Anytime you have human interaction with it.
Oh yeah, human beings are awesome sources of entropy, actually.
When we were doing the random number generator, we seed it with however many seconds when you hit the button.
Yeah. So SRAM time is kind of a default way to. So SRAM time, there's good and bad things about it, right? That it's not terribly predictable. The bad thing about it, there's a series of bugs where basically people realize that they could totally decrypt all the traffic coming out of Netscape, because if your machine was like NTP, like Network Time Protocol, synchronized, they know exactly what time it is on your machine. If they see a network packet like going out to Amazon.com, they know exactly when it started doing the encryption to do that. So it's like they could just repeat that entire calculation starting from time. The big problem with time is it has integer granularity, right? So it's number of seconds. There's a huge problem in the Ubuntu where, so this Netscape 4, this was like, they realized like, whoa, we can't possibly do that, right? It's fine if you want like it to look different every time you run the program. That's definitely plenty good. But if you want actual like cryptographic randomness, this is not nearly good enough. So similar deal, actually the Debian version of OpenSSL, they had actually tweaked the SSL. OpenSSL it's the standard SSL implementation used by virtually everybody, and it's just the most horrible like implementation you can imagine. It's a total mess. The Debian guys were actually going through and trying to clean it up. So they actually tried to find places where like it failed Valgrind. Like Valgrind was like, yeah, that value's uninitialized. Don't read that. And they went through and basically just said like, if you're reading uninitialized memory, something's wrong. And they basically patched the code to try and fix it. And it turned out it was a false positive. That version of OpenSSL was basically using uninitialized memory as a sort of source of randomness. It's not a very good source of randomness because the program is usually fairly predictable what the heck is happening. But part of the stuff in there was an actual true source of randomness, which they ended up commenting out. So all they were left with as far as actual randomness in the OpenSSL keys was the process ID, and the process ID is a 32-bit, or it's a 16-bit number, right? There's only like 30, the process counter goes to 32,000 and then wraps around, which is like, whoa, I mean, stupidly tiny keys. And it took years for this to be noticed, right? That like, there's only 32,000 keys that my Debian machine can generate. Yeah, so.
If someone restarts their computer multiple times.
Yeah, and the problem is like, if I do a test where I'm like, I'm gonna generate 10,000 keys, bam, 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 right? Separate process ID, I'm gonna get totally unique keys. First time I do this, and then if the second time I do it, maybe a server's been running longer, and if I haven't rebooted, I'll get another set of unique keys, and it's only going to wrap around after 32,000, which is a big enough number. So the problem is process ID, time, not good sources of randomness. The exact time, like down to the nanosecond for when any IO event happened is actually relatively okay. Right, how many clock cycles when the network interrupt came in, when the mouse moved and the keyboard went down, right? That those are actually decent sources coupled out to the physical universe, basically, because everything in computer is really deterministic, right? I mean, if I take 10, it's designed to be deterministic. So if you want real randomness, you have two options: dev random, and dev random source of randomness. And you notice what happened here. It spat out some crap, and then unless I like waggle the mouse around, it sort of has a very low rate of generating randomness. So dev random is the ultra paranoid one. They named it dev random because it's the easy one to remember. And then there's dev urandom, and the dev urandom is kind of the quick and dirty version. So the quick and dirty version meaning that it'll just keep spitting out crap at a maximum rate. Dev random estimates how much randomness it's emitted. And then when it doesn't really have enough left in its internal pool, it stops giving out numbers, it blocks. But it turns out the way dev urandom actually spits out its numbers is via like there's a it's inevitably going to be this is the infinite monkeys theorem, right? It's just going to be bashing away at output, and eventually I guess you could pipe it to string. So cat dev urandom pipe to string, and it's just like there's all kinds of printable stuff in there because you can pull out 100 megabytes per second or something of random numbers, and these are quite good actually. So dev random versus dev urandom. Dev urandom actually uses like a SHA-256 hash of the entropy pool inside the kernel. It's updated every time you touch anything or do any I/O operation. Dev random uses the same exact pool, but it keeps track of how much entropy is really left in the pool. So from some theoretical point of view, like taking the SHA-256 hash doesn't change the amount of entropy. It just changes the label you put on it. So in theory, somebody could look at your SHA-256 stream, right? There's the stream of dev urandom, figure out what your entropy pool was, and then be able to predict you from that point on. In theory, absolutely not possible. In practice, if somebody can do that, give up. You have no hope of protecting yourself against them. Because SHA-256 is, so we haven't even talked about it, but it's such a good hashing algorithm, nobody has actually found two things that have the same SHA-256 hash. That's how hard it is to, and if somebody could find that, their name would be remembered in Wikipedia forever.
Somebody's found it and told somebody, I guess.
Yeah, maybe somebody secretly knows.
Yeah, maybe.
Yeah. Well, there's people looking for it, and I'm guessing the only people who would have found it are like government agencies.
Yeah, so for example, if you could just take numbers and then make the SHA-256 checksum come out to whatever value you wanted. For example, you could mine bitcoins you could just win on mining bitcoins. So you mine all the bitcoins basically, because finding SHA-256 checksums that have lots of zeros at the start is the thing for winning winning block of mining bitcoins. So yeah, my recommendation is. Dev urandom. Dev random should only be used. It should not be used. Right? Because the deal is dev urandom is just as good. So it's spitting out all sorts of stuff. Now the thing is, the printable ASCII, but it's not that good. Right? So. Right. So dev urandom on Linux, there's a cryptographic randomness source on Windows. It does pretty much exactly the same thing. And you just say how many bits you want, and you can get really honest to goodness, pretty dang random stuff. If I run this again, right, you will not see. So if I run this, I want YE8. So I'm going to copy that pipe to less. So I can say, how often does that happen? Still looking hundreds of megs per second or chewing through there. It's eventually guaranteed to happen, but it should, I bet you will happen exactly as often as it should, which is not that often. Right, five-digit thing, random bytes. It's probably not going to happen while we wait here. So 5 random bytes. How bad is that?
No, just
5 random bytes is 40 bits worth, right? So after doing 1 trillion of these, you should be there. We may be a while.
See move too. With an O and a 0. Sorry. Question mark. Move?
Okay, questions about this? So entropy, definitely a thing. I need to give you a homework, and it's going to be on one of these sorts of things. I was going to do the what's wrong with these numbers, but realizing that would be kind of cool.
I'm down for sitting here.
Newspapers in a room going insane.
World
World War
War
II cryptographer level.
Mm-hmm. Yeah, beautiful mind.
Beautiful mind. That was our movie.
What's wrong with these numbers? They're not in a good human readable format. Done.
Okay. Yeah. Let's see. So if you're still tuned in, can I add you as a presenter? And if so, how? Okay. Viewer versus presenter. I add presenters when I start the broadcast. Probably similar. Another alternative is we just give up on doing Google Hangouts on air. We just switch to Google Hangouts.
That's not right. The exam example was like a really good one, I thought.
I remember I called it the Microsoft one time because like my key wasn't working for some when I actually had a key for Windows. They were like, "Yeah, we're pretty sure it's not a Z. We don't have Z's in our keys." I was like, "That sounds like a really bad thing to tell." But
Well, I have to add you during the broadcast.
Mate. GENs, that's how they used to work. It's like
Yeah, I see. So I must have added you guys on the announce.
It's why you can get like a key generator for your old Warcraft 3 game. I was like, I got this from a friend, but we want to play together. So I'll just generate my own key. That way the game doesn't detect that we're both playing on the same key.
Yeah, but where's the fun in that when you crack the EXE, not use the key?
Did they remove
I mean,
that?
the whole point of getting together was play the game,
Although then
not
you
play hacking the
also-
program.
You're also like the most like lazy, like, yeah, just copy the file from us. We don't care.
Added benefit, you get like you get a shell running on your computer for like some guy in Romania. It's awesome. It's
Oh, yeah,
like,
totally.
yay!
And
What
just
would
listen
you
to
rather
the
have?
music for
I don't know, man. That's
I see many things in here, and I don't know what. So what's funny is in control room, you would think that I could add people, and all I see in control room is me. The problem is y'all are viewers, and I don't know how to make you not be viewers. What? Oh, and Keys has my. Sorry, we just lost video. Okay, yeah. So what, do we just give up on Google Hangouts on air? I'm totally down with that. It would be kind of nice to have the archival part of this, but it's not totally necessary. And I think the experience for y'all tuned in live is really not nearly as good as with the just Google Hangouts. There's a Q&A. Yeah, there's a million options on here. Oh, as guest join, hide their audio and video. No. Broadcast the large video I see to my audience and hide other video feeds. No. New guests on my large broadcast are muted when they join. No. Yeah, so I just I don't see it on Cameraman where I could make you guys actually be able to say anything. Yeah, silly. You would think this stuff would be easier. Yeah, you'd think I'd be able to like click on viewers or somehow that I could. Cameraman. Yeah, control room still. The problem is you show up as viewers rather than as potential sources or participants in the Google Hangout. It makes me wonder if I should have sent you some different link to like a participant link instead of the just the Joe Schmo viewer link. Yeah, I think we'll just go with a regular Hangout next time. So thanks for calling in.